Welcome to the video lecture series for Texas A&M University Course Math 152. Today we will look at section 8.3, Trigonometric Substitution. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. There are quite a few questions in the warm-up to remind us about solving trigonometric equations, some inequalities, restricting the domain of the trig functions to make them one-to-one, and finding the domain and range of the inverse trig function graphs, as well as reminding ourselves of the Pythagorean trig identities. We will skip ahead in the video to the part that begins at the calculus that involves all of this warm-up or pre-calculus and calculus 1 material. However, you can scroll back through the warm-up and find the answers at a later point. I recommend that you make sure you do the warm-up first on your own and check your answers before proceeding. So we are now at the section 8.3 Trigonometric Substitution, where we have warmed up the pre-calculus, the trigonometry, and the calculus of inverse trig functions, and so on. When we see the expression square root of a squared minus x squared, where a is going to be a constant, and we see this, we should be reminded of the trig identity that cosine squared of theta is equal to 1 minus sine squared of theta. And we are going to make the alignment with x squared being sine squared of theta, except we also have to have a factor of a. So we are going to let let x equal a times the sine of theta. And the restricted domain is going to be, ultimately we're going to be talking about solving for theta. And when we solve for theta, we get, first of all, sine of theta is equal to x over a, and therefore theta will be sine inverse of a ratio x over a. As a result, the restricted domain of the sine function is the angle set contained from negative pi by 2 to pi by 2. In the next case, when we see the square root of a squared plus x squared, that reminds us of another trig identity. Namely, if we have sine squared theta plus cosine squared theta equal to 1, and we divide everything by cosine squared theta, this gives us the trig identity of tangent squared theta plus 1 is equal to secant squared theta. And so we're reminded of the fact that secant squared theta is equal to 1 plus tangent squared theta. So we are going to let x equal a tangent of theta, and the restricted domain for tangent theta is from negative pi by 2 to pi by 2, excluding the endpoints. Lastly, when we see the variable squared minus a constant or a constant squared and then square rooted, we think of rearranging this identity, which says that tan squared theta is equal to secant squared theta minus 1. And from here we are going to let x equal a times the secant of theta, where theta is contained from 0 to pi by 2, excluding the pi by 2, union pi by 2 to pi. Okay, let's take a look at an example. Determine the integral of the square root of 9 minus x squared all over x squared dx. In this case, we have the constant minus the variable term squared, so it reminds us of cosine squared theta equal to 1 minus sine squared theta. And so our choice is going to be that we let x equal, a is equal to 3, because 3 squared is 9. So x will be equal to 3 times the sine of theta. Now this is a substitution, but the difference is that the old variable is isolated. Whereas in the past, we always let the new variable u or t equal some expression of x, where x was the original variable. So technically, if we wanted to think of it as a method of substitution like 6.5, we would be saying let theta equal sine inverse of x over 3. However, most people are more comfortable with the trig expression, and it's easier to do the derivative in order to calculate dx and d theta. So we don't use it in terms of isolating for theta, as we did do in 6.5, method of substitution. So let's get rid of this. We don't need this. And of course, we need to identify the differentials. Dx will equal 3 cosine of theta d theta. And from here we can do the substitution. So the integral, I'll put the integral here, is equal to, I'm changing the variables, and I'm going to rewrite it in terms of theta. The integral of the square root of 9 minus x squared, which will be 9 sine squared theta, all over x squared, which will be 9 sine squared theta, multiplied by dx, which is equal to 3 cosine theta d theta. The numerator, we can factor out a 9 as a 3, and then we are left with the square root of 1 minus cosine squared theta, all over 9 sine squared theta, times 3 cosine theta d theta. We can reduce the 3 times 3 in the top with the 9 in the bottom, and we can notice that the square root of, or 1 minus cosine squared theta, my apologies, this should say sine squared theta, getting ahead of myself here. 1 minus sine squared theta is cosine squared theta, and the square root of cosine squared theta is the absolute value of cosine theta. However, we are going to be dealing on restricted domains, appropriate domains, and getting the outputs of the differential to match, and we will not be needing the absolute value in these examples. So we have the integral of cosine theta times cosine theta makes it cosine squared theta over sine squared theta d theta, which is cotangent squared theta d theta. Now this may or may not be a basic integral. If it is, then we're done. But if cotangent squared theta is not some basic function's derivative, in other words, if cotan squared theta does not have a basic antiderivative, then we will have to do some other technique. The techniques we know are method of substitution, we know integration by parts, we also know we could use trig identities like we saw in 8.2, trigonometric integrals, or we could use trigonometric substitution. Well, in this case, since we don't have a basic antiderivative, we would have to do some other technique. Well, we can see that we've got an inner function of cotangent theta and then an outer function of squaring, which suggests we could perhaps use method of substitution. However, we don't have anything else multiplied by the d theta, so that might not present a logical strategy. We could deal with trig identities. We know one for cotangent squared of theta. However, that would involve cosecant squared of theta, which we don't necessarily have an answer for. Or do we? Well, if we rewrite this, we get the integral of, let's just take this identity, and if we divide it all through by sine squared of theta, we get that cotangent squared of theta is equivalent to cosecant squared of theta minus 1. And while cotangent squared of theta is not a basic antiderivative, cosecant squared theta is. It is someone else's derivative. The question is who? Well, if we recall, the derivative of cotangent x is equal to negative cosecant squared of x. And so this is a good option. Let's use a trig identity substitution for cotan squared x, and we get cosecant squared of theta minus 1 d theta, and the antiderivative of cosecant squared theta is negative, the antiderivative is negative cotangent of theta, and then the antiderivative of minus 1 with respect to theta is minus theta, plus a constant. So we back substitute, and of course, if x is equal to 3 sine theta, we know that sine theta is equal to x over 3. And as soon as we see that information, we can and maybe should draw a triangle. And label all of the sides. Continuing to solve says that theta is equal to sine inverse of x over 3. And the cotangent of theta is going to be adjacent over opposite. So we get negative the square root of 9 minus x squared, all divided by x. minus theta, which is sine inverse of x over 3, and then plus a constant. So if this is a function f of x or y, let's take the derivative of it and confirm that we get the original integrand expression. So if we let y equal negative the square root of 9 minus x squared all over, I think it was just x, minus sine inverse of x over 3, and then plus a constant. Therefore, y prime is going to equal, I'm going to write this as 9 minus x squared to the exponent 1/2, will be negative 1/2 times 9 minus x squared to the negative 1/2 multiplied by negative 2x is the derivative of the top times the bottom minus, so minus and negative will be plus, the top times the derivative of the bottom, which is just the square root of 9 minus x squared. And then we have all over the denominator squared. And that will be minus also the derivative of sine inverse of stuff, which will be 1 over the square root of stuff. In this case, this 1 over the square root of 1 minus stuff, multiplied by the derivative of stuff. And the derivative of x over 3 is 1/3. The derivative of a constant is 0. I'm going to need to do some simplification. I'm going to multiply the top and the bottom by 9 minus x squared to the positive 1/2 of the first fraction. And I can simplify the negative 1/2 times the negative 2. And I have an x squared to be multiplied together here. So this is going to give me that y prime is equal to 9 minus x squared to the negative 1/2 times the red numerator gives me 1 times x squared. So we get x squared plus something multiplied by itself, keep the base and add the exponents. So we get 9 minus x squared. And that will be all over x squared times the square root of 9 minus x squared. And here we get minus 1/3 times the square root of 1 minus x squared over 9. So inside here I'm going to make this 9 over 9, and I'm going to get 9 minus x squared all over 9 under the square root. So then the 9 comes out in the denominator as 3, and 3 divided by 3 reduces. So here we get 1 over the square root of 9 minus x squared. So now we need to multiply the second fraction in the top and in the bottom by x squared to get a common denominator. So now the common denominator is x squared times the square root of 9 minus x squared, and we're going to get 9 minus x squared to the exponent of 1. And so we keep the base for these division, and we get 9 minus x squared to the exponent of 1 minus 1/2, which is 9 minus x squared to the 1/2, or square root of 9 minus x squared all over x squared. And we can see that that's the same as the expression we started off in the question, and so our antiderivative is correct. All right, let's evaluate the integral from 0 to 5 of the square root of 25 minus x squared dx by two methods. We are still reminded of the 1 minus sine squared theta identity. So we are going to let x equal a, which is 5, times the sine of theta. And dx is equal to 5 cosine theta d theta. Furthermore, we have a definite integral. So when x is equal to 0, we have x equal to 0, which equals 5 sine theta. And therefore we know that theta is equal to 0. When x is equal to 5, or when 5 is equal to 5 sine theta, we know that sine theta must equal 1, and therefore theta on the restricted domain is pi by 2. So we can change the integral here to equal the definite integral from 0 to pi by 2. Inside here we're going to get 25 minus 25 sine squared theta, which is going to give us a simplification we multiply by dx, which is 5 cosine theta d theta. And the 5 will come out of, the 25 will come out as a 5 times the other 5, gives me 25 in front of the integral. The square root of 1 minus sine squared will be cosine theta times cosine theta, which is cosine squared theta d theta. Now, recalling our trig identities, we can recall that cosine 2 theta is equal to cosine squared theta minus sine squared theta. And using the Pythagorean identity, we can express this as 2 cosine squared theta minus 1. So we can solve for cosine squared theta as 1 plus cosine 2 theta, all divided by 2. And so this is a simple or basic antiderivative. 1/2 is a constant, and cos 2 theta over 2 has an easy antiderivative. So we can substitute the trig identity for cosine squared theta as 1/2 plus 1/2 cos 2 theta d theta, which gives 25 times theta plus sine 2 theta divided by 2 multiplied by 1/2 is 1/4 sine 2 theta, evaluated from 0 to pi by 2. So we get 25 times pi by 2 plus 1/4 of sine pi, because we double pi by 2, minus 0 for theta, plus 1/4 sine of 0. Sine of pi is 0, sine of 0 is 0, and so the final answer is 25 pi by 4. And this is method 1. If we go back and try to understand what the definite integral represents, then we can see in method 2 that we have a function f of x or y equals the square root of 25 minus x squared, which, if we square both sides, gives us the equation for a circle with a center at 0, 0 and a radius of 25. And therefore, the function f is the top half of the circle centered at 0, 0 with a radius of 5. So when we set up the definite integral, if we take a look at that picture, there's f of x from -5 to 5 along the x-axis. However, the definite integral is only looking at going from 0 to 5. And so we're talking about the area, because we have positive width from 0 to 5, as well as positive height. So this definite integral represents the area from 0 to 5 of f of x dx. It's the area of a quarter circle. So 1/4 pi r squared, where r is equal to 5, gives 25 pi over 4, which is the same answer. In example 2b, determine the area of the ellipse given by x squared over a squared plus y squared over b squared equal to 1. Well, x over a all squared plus y over b all squared equal to 1 is a scaled version, non-uniformly, so we're not scaling horizontally and vertically the same amount, from the unit circle, x squared plus y squared equal to 1. So we know the unit circle looks like this, and depending on whether a is bigger than b or vice versa, we could have an ellipse that's horizontally or vertically oriented at the same center. So it really is not important whether the a value or the b value is bigger, but in the red case, a is bigger than b, and in the green case, b is bigger than a. So we want to determine the area, so we can look at 1/4 of the area and multiply by 4. So we can say that area of the ellipse is 4 times the definite integral from 0 until this point, which used to be 1 comma 0, but has been scaled or multiplied horizontally by a factor of a. So this is the point a comma 0. So from 0 to a of the function. So we need to solve for y. So we know that y squared is equal to b squared times 1 minus x squared over a squared. And I can get a common denominator here, so making this b squared over a squared times a squared minus x squared. And then when we take the square root, we're going to get plus or minus the square root to give us a top half and a bottom half, and we are going to use the top half with the positive square root. So we're going to have positive square root. We can also take the b squared over a squared outside. A and b are both positive numbers. Even if they weren't, after squaring they would be, and we're just talking about a horizontal scaling and a vertical scaling. If a and b, or only one of them, were negative, it would mean that we have a horizontal or a vertical reflection, which, because of the even symmetry of all three of these quadratic relations, the circle, the green ellipse, or the red ellipse, it doesn't matter if there's a reflection involved because of the even symmetry, the mirror image about the y-axis. So for that purposes, we can take a and b to be positive constants. So they can come outside of the square root, leaving us with this expression for the top half, the positive root for the top half of the curve. And so b and a are constants, so we can make this 4b divided by a times the integral from 0 to a of the square root of a squared minus x squared dx. Then we are going to let x equal a sine theta, which implies that dx is going to equal a cosine theta times d theta. And when x equals 0, that implies that theta equals 0. And when x equals a, that implies that theta is equal to pi by 2. And that makes sense because theta is going to be a quarter turn or a quarter revolution through the curve in red. So therefore, the area of the ellipse will be 4b over a times the integral from 0 to pi by 2 of the square root of a squared minus a squared sine squared theta, which is going to be a cosine theta, multiplied by dx, which is another a cosine theta d theta. One of the a's in the top and the bottom reduce, and we're left with 4ab times the definite integral from 0 to pi by 2 of cosine squared theta d theta. So therefore the area can be rewritten as a definite integral involving a trig substitution like we saw in the previous example, which is now a basic integral. So we get 1/2 theta plus 1/4 sine 2 theta, evaluated from 0 to pi by 2. And if you recall, this expression worked out to be pi by 4. So we're going to get 4ab times pi by 4, which is equal to pi ab. And so in general, whenever you have an ellipse with a horizontal radius of a and a vertical radius of b, the area of that ellipse, no matter where the center is, could be located at h comma k. And so the equation of the ellipse might be this. It's only the dimensions a and b, the width, the semi-major radius, and the semi-minor radius that are important. Furthermore, if a is equal to b, then the area of an ellipse really turns into the area of a circle, and we get pi a squared, where a, of course, is the radius of the circle. In example 3, determine the integral of 1 over x squared square root of x squared plus 4 dx. Now here we see that we've got the variable term first squared plus a constant, and this reminds me of tan squared theta plus 1, or 1 plus tan squared theta, depending on how we want to write it. And this is equal to secant squared theta. So I'm going to let x equal a, which is 2, tan of theta. And therefore dx is equal to 2 secant squared theta d theta. So doing this substitution, we get the indefinite integral of dx, which is 2 secant squared theta d theta, divided by x squared, which is going to be 4 tan squared theta, times the square root of 4 tan squared theta plus 4. And we simplify the square root, and we can reduce the 2 and the 4. And if you want, you can take that 2 in the denominator outside as a 1/2. So we have secant squared theta d theta times tan squared theta times square root of 4, which is 2, and then tan squared theta plus 1 is secant squared theta. Coming out of the square root will give us secant theta. And we can reduce here. I forgot my 1/2 in red, and I can take this 2 out front as well, giving me a total of 1/4 for the coefficient. And we have secant theta d theta all over tan squared theta. So at this point, we could try recognizing this as a basic integral. We could try method of substitution. We could try integration by parts. We could use some trig identities. Or we could try another trigonometric substitution. However, this seems unlikely because we don't have the square root of one of these 3 basic expressions. If it's not obvious, maybe you want to rewrite it in terms of sines and cosines. This is a good strategy that we see in pre-calculus when we are proving trig identities. And so tan squared theta is really sine squared theta over cosine squared theta, which means that the cosine squared theta can come up in the numerator, and the secant theta can come down as a cosine theta. Or one of these can reduce with this, and so we are left with cosine theta divided by sine squared theta d theta. Now you really need to try these rather than memorize what I'm doing, because there is some instinct based on having a set of knowledge, the trig identities and the different methods. You also need to know your basic derivatives so that you can recognize if you need to use a method of substitution. Here I see that I could use a trig identity, but I don't like having 2 terms in the denominator if I can help it. So I could replace sine squared theta with 1 minus cosine squared theta, but again, I don't like having 2 terms in the denominator. What I do notice is that sine squared theta is really sine theta squared, so I have an inner and an outer function. And furthermore, if I take cosine theta d theta as a unit, and I let that be dt, for example, this would suggest to me that t should equal sine of theta. And since sine of theta is an inner function, it seems like we should use method of substitution. So we get 1/4 times the integral of dt over t squared. And the denominator gives t to the negative 2 dt. So we get negative 1/4 t to the negative 1, or negative 1 over 4t, plus a constant. And then we back substitute. So we get negative 1 over 4 times t, where t is sine theta. And if you want, you can write sine theta as cosecant theta in the numerator. And then we have to go back and substitute theta in terms of x. So as always, as soon as we do a let statement involving a trig function, we should be drawing a triangle. So we have that the opposite is x, and the adjacent is 2, making the hypotenuse the square root of x squared plus 4, which is the expression that is coming in. So it shouldn't be a surprise when you see this expression over and over again. And then from here, cosecant theta is the hypotenuse over the opposite. So we are going to get negative 1/4 times the hypotenuse of root x squared plus 4 all over x. All over 4x and then plus a constant. Again, let this be a function or let this be y, take its derivative, and confirm that we get the integrand function in the original question. In example 4, we want to determine the integral of x over the square root of x squared plus 4 times dx. Well, it looks like x squared plus 4, the same as the previous one, so we might start off by saying let x equal 2 tan theta. But there is something different between example 3 and example 4. In example 3, we had an x squared in the denominator, and example 4, we have an x in the numerator. And we see that we have x dx as a pair, or as a factor multiplied together. So if this, for example, were dx, we would, or sorry, dt, some substituted variable, we might expect t to be some kind of quadratic function, ax squared plus maybe a constant for t. And since we have x squared plus 4 in the denominator, maybe we don't need to use the trig substitution. Maybe we can use regular method of substitution. So let's try. Let t equal the inner function of x squared plus 2. Because we have a quadratic inner function and a linear times dx, this is suggesting that regular method of substitution is a good approach. So unlike trig substitution, where the original variable is isolated, in regular substitution, the new variable is isolated, expressed as a function of the original variable. So here we can see our unit x dx, and we can replace it with 1/2 dt. So using this substitution, we have 1/2 in front of the integral, x dx is dt, and the denominator is the square root of t. So we get 1/2 times the integral of t to the negative 1/2 dt, which is 1/2 times t to the 1/2 divided by 1/2, or times 2, and plus a constant. And so the square root of t is the square root of x squared plus 4 plus a constant. So the point here is, don't always just start off with the most recent technique. Think about other possibilities. It would have been difficult if we proceeded here maybe to get the integral to work out properly, because we might not have had a nice number of tangent squareds or secant squareds or whatever it is. Again, take your final answer, set it equal to y, find y prime, and confirm that it is the integral function given in the question, or the integrand. In example 5, we now have the third variation. We have x squared minus a squared. So we had the constant minus the variable squared. We had the variable squared plus the constant, which is the same as square root of a squared plus x squared. And now we have square root of x squared minus a squared. So this is suggesting the third and final method of substitution, or rather trig substitution technique. We are going to let x equal a times the secant of theta, and in this case a is actually called a. So then we have that dx is equal to a secant theta tangent theta d theta. So in the integral we get dx divided by the square root of x squared, which will be a squared secant squared theta, minus a squared. The a squared can be factored, leaving us with secant squared theta minus 1. A can come outside of the square root as the absolute value of a, but since a is positive, the absolute value is not necessary. And then the a in the top and the bottom can reduce. Furthermore, in the denominator, we can use the trig identity, the Pythagorean identity, which says that secant squared theta minus 1 is tan squared theta, and the square root of tan squared theta will be tan theta. And we can reduce the tan theta and have to work out the integral of secant theta d theta. Now this is one that I asked you to memorize, add to your basic antiderivative or basic integrals. However, we did something in section 8.1, I believe, where we multiplied the top and bottom by secant theta plus tangent theta. Or rather, maybe it was method of substitution where we did this before. And we ended up converting this to an integral that we could use substitution on, and we found that the answer is going to be the ln of the absolute value of secant theta plus a constant. So you should recall this process when we multiply this through, and we could do a substitution for the denominator. Rather, it's ln of secant theta plus tangent theta, and then plus a constant. Then we have to back substitute, and doing so means that we need to be able to draw a triangle and come up with the various trig functions in terms of theta. So we have the angle theta, the hypotenuse over adjacent, if we divide by a, is x over a, and the missing side is going to be square root of none other than x squared minus a squared. And so from here we see that secant theta is x over a, and tangent theta is square root of x squared minus a squared all over a. So I get the ln of x over a plus square root of x squared minus a squared all over a. So I'm going to get a common denominator. And then plus a constant. So you should be able to take the derivative of this final result and confirm that we get 1 over square root of x squared minus a squared. In example 6, we want to evaluate a definite integral, and we see that we have 4x squared plus 9. The first thing I'm going to do is rewrite that so that we have the 4 divided through. We don't actually have to, but I think it's nicer to have a coefficient of 1 here. So in fact, without the bounds for a moment, well, with the bounds, I'm going to rewrite this as x cubed, and then I'm going to have 4 factored outside of x squared plus 9 over 4, all to the exponent of 3 halves. So the exponent of 3 halves tells me that I take the square root and then I cube. So I can take the square root of 4, which is 2, and then cubing, which is 8. So that 8 is going to be in the denominator. And I have x cubed dx still in the numerator, and then I have the square root of x squared plus 9 over 4, and that quantity is cubed. So I could do a method of substitution with x squared plus 9 over 4, or I could, which means that I could write x cubed in the numerator as x squared times x. So maybe a regular substitution would work, but maybe we have to use trig substitution. I'm going to leave you to think about this for a few moments. Please pause the video and try a regular method of substitution and a trig substitution. Okay, just pause the video and try both of these. Okay, if we were to let t equal x squared plus 9 over 4, then we would have certainly that x squared is equal to t minus 9 over 4, and we would also have that dt is equal to 2x dx. And we need x dx, and then this becomes x squared times x dx. Let me just write that, pulling it apart. X squared times x dx. So we certainly have the x dx here, and we have the value for x squared is t minus 9 over 4. So if we use the method of substitution, we get 1 over 8 times new bounds. I'm just going to, for now, call this x equals 0, and x equals 3 root 3 over 2. Then x squared is t minus 9 fourths, and x dx is equal to 1/2 dt. So if I make the 1/2 out front, this becomes 1/16. And then I have dt, and it's all divided by t to the exponent 3/2. That t can divide into the two terms in the top, which seems manageable. Meanwhile, if we use trig substitution, we would be letting x equal 3/2 secant theta, which means that dx is equal to 3/2 secant theta tan theta d theta. And the integral would turn into 1 over 8 times the definite integral whose bounds I still have not changed. And we would have x squared, which would be 9 over 4 secant squared theta, times x dx, which would be 3 over 2 secant theta times all of this. So let's start writing it down. We'd have 3/2 secant theta all squared times, I guess it's cubed, so I could just make it all cubed, times dx. So x cubed times dx is going to be times 3/2 secant theta tan theta d theta all over the square root of x squared plus 9 over 4. So we're going to get the square root of 3 over 2 squared is 9 over 4, which is going to factor out, leaving me with secant squared theta plus 1 under the square root, and that quantity all cubed. Which one, the red one or the green one, looks simpler and manageable? I think the red one looks manageable, but the green one, if it works, if it's easy for us to do, we should be able to simplify and expand. For example, the square root of 9 over 4 has to be cubed, so we can't just cross out the 9 over 4 under the square root with the 3/2. Do be careful, simplify this, and check to see that you get the same answer in both ways. I personally like working smarter, so just because I'm learning about the trig substitution doesn't mean that I forget method of substitution. So I get 1 over 16, I'm going to call this the definite integral from a to b, and I'm going to go back and change this expression in terms of x because I don't want right now. Actually, it might not be so hard. Let's change the bounds to t bounds, since I've committed to using one method over the other. So when x is equal to 0, t is going to equal 0 squared plus 9 over 4, which is 9 over 4. And when x is equal to 3 root 3 over 2, t is going to be this quantity squared plus 9 over 4. So 3 over 2 squared is 9 over 4, times another 3 is 27 over 4, plus 9 over 4, which is 36 over 4, which is 9. So those bounds aren't so bad. 9 over 4 to 9. T divided by t to the 3/2 is t to the negative 1/2, minus 9 over 4, t to the negative 3/2 dt, and by the power rule, this is a basic antiderivative or integral. So we get 1 over 16 times 2 square root t. This becomes t to the negative 1/2 divided by negative 1/2. Dividing by negative 1/2 is the same as multiplying by negative 2, so we get plus 9 over 2, and this is still t to the negative 1/2, or dividing by root t. So I'm going to make this plus 9 over 2 square root of t, evaluated from 9/4 to 9. So we get 1 over 16 And we get 2 times the square root of 9, which is 3, plus 9 divided by 2 times the square root of 9, which is 2 times 3. So the 9 and the 3 reduce, giving me 3 over 2. And in the second term, the square root of 9 over 4 is 3 over 2. Multiplied by 2 is 3. And then we have the square root of 9 over 4 in the second term is 3 over 2. But that is in the denominator, so we're going to have 9 over 2 multiplied by 2 over 3. So again, the square root of 9 over 4 is 3 over 2, but then we multiply by the reciprocal. So when we do that, the 2's reduce, the 3 and the 9 reduce, and we get 3 plus 3 is equal to 6. So we get 6 minus 6, and then 3 halves, 1 over 16 times 3 over 2 is 3 over 32. So you could try the green integral and compare your answer. You can also check your answer on the TI Inspire and make sure that you're getting a definite integral of 3 over 32. The point of this exercise is not to just use the most recent method, but to consider your different options and under which circumstances each of those options applies. In the last exercise, we want to determine the integral of x over the square root of 3 minus 2x minus x squared all times dx. Well, here we recognize we need to complete the square, otherwise we can't see the forms x squared minus a squared, x squared plus a squared, or a squared minus x squared. And so completing the square means that we will take 3 minus 2x minus x squared, and I am going to rewrite the quadratic and the linear terms with the coefficient factored outside. Then I'm going to add and subtract something. I take half of the linear coefficient and square it. Half of 2 is 1, squared is 1. I add and then subtract. And so then we have 3 minus x plus 1 quantity all squared minus 1, which is going to give me 4 minus x plus 1 all squared. So now we have the integral of x over the square root of 4 minus x plus 1 quantity squared, and then times dx. So if you don't like this because you're used to having just an x under the square root that is squared, you could do a change of variable. You could say let t equal x plus 1, therefore x is equal to t minus 1, and furthermore dt is equal to dx. And you could change this to the integral of t minus 1 over the square root of 4 minus t squared times dt. This form then looks like this form, which suggests that x or t should be a sine theta. So if we do that, just trying to make this a bit tidier. Well, we'll leave it. This is going to equal, this here we're going to say we'll use a different variable, or we'll use t rather, equal to 2 sine theta. So dt is equal to 2 cos theta d theta. And therefore this integral is now equal to the integral of 2 sine theta minus 1 Well, actually, before we proceed, I want to maybe break this apart. The reason I want to do that is because I remember example 3. If we go way back to example 3 and contrasted it with example 4, in example 3 we had a constant over square root of x squared plus 4, and in example 4 we have a linear over square root of x squared plus 4. The linear was a good indication that we should do a regular method of substitution. So because I have linear over square root of 4 minus t squared, maybe the first term in the integral can use a regular method of substitution. So before I transform or change this in terms of the green information, I'm going to rewrite this blue integral as the integral of t dt over square root of 4 minus t squared minus the integral of 1 dt over square root of 4 minus t squared. And now, from here, t dt over square root of 4 minus t squared, we can use regular substitution. We haven't used m. Let m equal 4 minus t squared. Therefore, dm is equal to negative 2t dt. And so this integral turns into negative 1/2 times the integral of dm over the square root of m. So we get negative 1/2 times the integral of m to the negative 1/2 dm, which is negative 1/2 times m to the exponent of positive 1/2 divided by 1/2, or times 2. And so this is equal to negative the square root of m plus a constant, which is equal to negative the square root of 4 minus t squared plus a constant, and t was x plus 1. Meanwhile, if we take the second integral, I'm just going to do the integral without the negative sign, dt over the square root of 4 minus t squared. We can use trigonometric substitution here and let t equal 2 sine theta. Therefore, dt is equal to 2 cosine theta d theta. So this integral becomes 2 cos theta d theta all over the square root of 4 minus, so I can factor 4 out, 4 minus 4 sine squared theta. The 2 in the top and the 4 under the square root in the bottom reduce. And we have cosine theta all over the square root of cosine squared theta, which simplifies to cosine theta. And this is equal to theta. And theta is going to equal sine inverse of t over 2. So this is theta plus c, which is sine inverse of t over 2, but t, we had said, is x plus 1. And so for our final result, which was the definite integral of x dx over the square root of 3 minus 2x minus x squared, we get the sum of these two integrals. Actually, the difference, if you recall, we had a minus sign here. So we get an answer of negative square root of, this inside works out to 3 minus 2x minus x squared, minus sine inverse of x plus 1 all over 2 plus a constant. So you have to make sure that you can do some of the basic algebra, you know your trig identities, you can draw a triangle or rearrange as necessary from the Pythagorean identities, and then sometimes go back and use earlier methods that we saw in the course so far. This concludes section 8.3, trig substitution. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.